NASA significant incidents report that comes out every 2 years, and it's probably due to be updated in the not too distant future.
If you'll give me one, I'll make sure my office
you
makes
can,
a copy.
And I can.
Those who don't have
It's available electronically, and I can send the link to you as well. The actual the Safety and Mission Assurance Office actually prints these out. So for the engineers that like to carry around this is the chart that talks about all the different bad things that have happened in spaceflight, and they're always a good lesson, especially for the human factors aspects of it. Yeah, so I have a few of those, and if anybody wants my business card and email me, I can send you more material. I actually have a Dropbox file. I put all the space safety stuff. Some of it is commercial, some of it is a lot of NASA lessons learned. My name is John Clark. Today we're going to talk about incidents in spaceflight, risk of human spaceflight. Depending on the time, I may be able to shorten some of this. I have a pretty extensive review on all the other things in life that can kill you, just so you have a perspective of what spaceflight can also generate. But if you have any specific questions or you want to go on my space safety Dropbox file, have at it. Just as way of background, I was a naval officer, most of it in aviation or medicine, for 26 years. I was at NASA here at JSC for 8 years. I was a branch head for medical operations and a shuttle crew surgeon. I was also involved in the spacecraft survival investigation team that came out in 2008 with the Columbia survival investigation report, and then most recently NASA published a book called Loss of Signal, which was the aeromedical lessons learned. That's available on the in the electronic format, and you can also buy a copy with the government printing office. I'm not sure where my AV guy went, so is there an alternative? I guess I can do it on memory stick if you want. I don't know if it'll work, but it's worth trying. Do you have the computer here?
Because I didn't bring my computer.
Yeah.
But this one, he's got hooked up with his.
Yeah. Well,
hold on, let me ask her, because she knows who the guy's name is. We don't know who it is who left here to go get the.
JT, I mean, if he knows to be finding it, he's looking for one.
it's always something, you know. We have this all advanced technology.
I said to her, I'm not going to bring my computer. Do I need to bring it?
In my in the old days, I used to use view graphs when you only had to worry about the bulb burning out. So they were really always a challenge. Well, does anybody have any questions before we start? What are your expectations?
But you're now, Dr. Clark, you were here, as I was saying when we walked in the door. You and I were out there in Building 37 eons ago.
Yeah.
And you're now at NSBRI.
Okay, so yeah, where I am now is I'm in Baylor College of Medicine, and we have a Center for Space Medicine, and I teach there, and I'm also in the neurology department. I also am the space medicine advisor for the National Space Biomedical Research Institute, which is a research arm for NASA, health and human performance. And I only there part-time because I'm doing a lot of commercial stuff. I do advise for a number of commercial space companies. I was the medical director for Red Bull Stratus. I've got another similar project ongoing as we speak. Also work with Inspiration Mars, which is a long Mars flyby mission, and gosh, who knows? I've got so many different irons in the fire, I can't always keep track of them. But I'm pretty busy on the commercial side of things, suffice it to say.
But you're still here in Houston.
Yes. Okay, so why don't we go ahead and I'm going to go through this pretty quick. I will make this stuff available for you all. So you don't have to take notes. This is the outline. I always like this quote. The only thing we learn from history is that we learn nothing from history. And I'm a big history buff, so a lot of the stuff that I do has to do with going and looking at lessons learned from history. These are the learning objectives. I'm going to just go through this real quick because we've got a pretty quick time frame. I thought it was going to be a 2-hour class, and now it's going to be a
Well,
little
we
bit.
have 2 hours for the room. I don't know how many people
Yeah.
can stay for the 2 hours.
Okay, so this is going to be the outline. We're going to cover a ton of different areas. Every year I kind of review how long we've been in space, and we're up to probably 120 person years in space. 500 plus people have flown in orbit. All the long duration record holders are owned by the Russians. Sergei Krikalev, who flew Mir and 2 ISS missions, has 800 total days in space. There are, I think, 8 people who've had over 500 days in space, and I think 4 people have actually flown 1-year missions or greater. And the longest single mission is Valery Polyakov, who's a Russian physician who flew 14 months in space. I break the hazards of spaceflight down into 3 general areas. We have the environment of space, we have the vehicle environment, and then we have the mission architecture. And those are different things that can conspire to affect human performance and health. You know, obviously the space environment with microgravity, radiation, debris, the vehicle environment, all the things that are result from being in a closed-loop life support system, and then the mission architecture, the things that we do to crew, such as make them work long hours, slam shift their circadian rhythm, and then various aspects. So I was going to just briefly go into some high-risk activities as comparison. These are some of the top risks with respect to activities that insurance companies charge more money for, like hang gliding, private pilot aviation, mountain climbing, skydiving, boating, motorcycles, et cetera, et cetera. And what you see there is that, some of these activities are considered high risk, but they're relatively safe. You know, 1 death in over 100,000 flights for hang gliders. For parachuting, it's about the same for every jump, 1 in 100,000. But if you base jump, which is from buildings or antennas, bridges, or earth, low altitude terrain following, stuff like that, it's a couple of times more fatal. There's 2 ways to categorize risk. One is by events or activity. You know, in other words, 1 accident per mission flown. The other way to do it is by participants. So, you know, if you look at something like base jumping, where there's not as many people that do it, a fatality of 1 in 60 base jumpers. This last year there was 24 deaths with base jumpers. Mountain climbing is another high-risk activity. It depends on where you go. These are deaths per 100 climbers, so this is based on the population. You know, if you climb Yosemite or Mount Whitney in California, you know, we're talking about 1 in 10,000 who climb Mount Whitney. In Yosemite, it's 1 in about 400 or 500. For the real serious stuff like Denali or Mount Rainier, it's in the order of 1 in 300 or less. But if you go to the Himalayas, it's huge. It's on the order of maybe 1 in 10 die going to the summit. That's pretty high. For K2, which is a little bit more dangerous, it's 1 in 6. It's like a Russian roulette. You know, and 1 year on K2, almost over half the people that went died. So that's playing Russian roulette with 3 of the 6 cylinders loaded. We'll talk a little bit about flying, because that's an area that when we compare risk in spaceflight, we have something to compare to. The risk in commercial flights, Part 121, the regular commercial airliners, they're really safe. They have failures of equipment in the 1 in 100 million flight hours, and they might lose an aircraft in a million flights. So it's pretty safe. In military aircraft, 1 in 100,000 flights, so just an order of magnitude more risky. When I flew combat in Desert Storm, loss rates were 1 in 3,200 flights, missions. So combat missions increase it. And now we bring it up a notch. Okay, what was it like in the really bad times? European theater, World War II, bombing missions, daylight missions, World War II. It was about 1 in 100. But early on, it was 1 in 25. Now, if you take the flight profiles that we've had generated enough numbers to calculate risk from, we have almost 200 flights of the X-15 program, suborbital missions, winged launch, air launch drop from a B-52. We had one fatal mishap and a couple of landing mishaps in 200 missions. So roughly 0.5%, 1 in 200 flights fatality. We had 135 flights of the shuttle, in the shuttle program, 2 lost vehicles and 7 crew per vehicle. And then we have the Russian blunt capsule. We have well over 110 flights plus their Progress, which is a similar vehicle. So they've lost two vehicles in about 116. So we can generate a profile that looks about, for suborbital, maybe 1 in 200, for orbital, between 1 in 70 to 1 in 100. So what that tells you is that the loss rate for spaceflight, so for orbital spaceflight, is about what the loss rate for a World War II daylight bomber crew in Europe was. Early on, it was 1 in 25. Challenger was the 25th shuttle flight when it went down. Columbia was the 113th. And this was a poster in the safety office here. And when I went by it and I saw it, I just about, my jaw just dropped off. That is exactly what our mission loss rates were. So when I work in the commercial sector and I talk to folks, I tell them, hey, this is risky stuff. Understand your loss rate is about what a bomber crew in World War II faced. And it was so bad in the European theater operations that there were actually mutinies by the bomber crew. They actually were they would lose 10% of their aircraft on every mission. That's the kind of fatality rates that we're dealing with. I won't talk too much about this, but it's not just flying in space that's dangerous, it's preparing for space. We lost Apollo 1 on a ground checkout, no intention for flight, so it doesn't count as a flight mishap. A lot of fatalities in training. Russians lost a guy in water survival training. They lost Yuri Gagarin in a aircraft fatality, and we lost 2 aircraft and 4 crew in the early space program. So we can lose people in training and ground operations as well. I'll cover very quickly where do we have concerns, and this is the rough area. If you look at that chart, you'll have the pre-mission phase, the launch part, the early ascent, rendezvous and docking on orbit, and activities like spacewalks, reentry, descent, landing, and post-recovery. So those are all the things that we could potentially lose crew. And you'll see that in this chart is not going to be something you're going to be able to see on the screen, but if you have a copy of it there, you can look at it. If you want, I can send you a JPEG file that's 12 megabytes, and you can blow it up. I actually have it blown up in my office. And what this tells you is that all these little, like the red outlined yellow boxes are the fatalities, and all these little things are things that happen, bad things that happen. Some are mechanical failures, many of them have human-related factors involved with them. But what the point here is that all the loss of life in the US and Russian side has not occurred in space, it's occurred in the atmosphere. It was either on the launch pad, during ascent, or during reentry and landing, because that's where the energy transfers are the greatest. You've got chemical energy going into kinetic energy, and you've got kinetic and potential energy in the form of altitude that you have to contend with and transfer to thermal energy. And so those energy transfer regions during launch, ascent, reentry, and landing are where we've lost all the crew. But most of the time crews spend in orbit, particularly these long duration crews, that's where the time frame for things that can happen in space. And we'll go through some of these as representative examples. I'd give another separate talk on crew survivability and escape systems. This talk is about all the ways you can die in space, and the other talk, the companion talk to this that you unfortunately won't get, is about how do you mitigate that risk, how do you reduce that, how do you keep crews alive when something bad goes wrong. And then These are the different things that you would do to address those different phases of flight. I'll point out a couple of really great references. There's the International Academy for the Advancement of Space, or Association for the Advancement of Space Safety has a book called Safety Design. They have one for space operations. They also have a commercial spacecraft guideline. These are two reports that I was involved with. The Columbia Crew Survival Investigation report that came out in 2008. And then this one just came out maybe a couple of months ago, called Loss of Signal, the Aeromedical Lessons Learned from Columbia. So let's get right into it. What's our biggest risk? Before we start the flight is the launch pad. And these are all the various health threats. You've got things that are too hot, things that are too cold, debris, toxic fumes, fire, falls, etc. The very first loss of crew or loss of people occurred in 1960. This was before the manned flights that Yuri Gagarin and the Vostok series underwent. It occurred in 1960 when they were testing a new booster, the R-16. Niederlein was the commander of Soviet rocket forces. And he combined two things that we know do not work well together. One is having dignitaries and schedule pressure and having testing and launching a new system. And so he made a cardinal error. This is so replete with human error, it's almost shocking. But what happened was they were working a vehicle problem, and they were actively working it while they had visiting dignitaries. They were trying to launch on an anniversary of one of the Bolshevik revolutions or whatnot. And they committed a fatal flaw. They didn't detank the vehicle when they were working on it. Detanking means defueling it. So you have all this, in this case they use liquid oxygen and kerosene, RP1. They decided, well, that's going to take time. We detank it. We're going to waste time. We want to launch. Pressure, pressure, pressure. Boom, boom. What happens is they inhibit the first stage, but as they're working on it, the second stage timer starts to count down. And it ignites while there's a huge number of people on the field, including General Niederlein, who died in the blast. 74 people are killed from the fumes and the fire, and then later another 48 people die. Here's a video of it that actually, yeah, I don't know if there's sound. All you're going to hear is people screaming and running. But basically, when this thing cooked off, there were people everywhere. Now, the Russians still, to this day, let you people walk around the vehicle with cigarettes, and we look back on that and just go, oh my God, are you kidding me? So anyway, that was the first loss of life that occurred, and we learned from that, follow procedures, don't have dignitaries there, put in schedule pressure when you're trying to work a problem, and press, and do the right thing. This is so now the next phase is a launch pad where there were crew on board. This was Soyuz T-10. They put the A on the end after the abort and launched another T-10 several weeks later. In this, Vladimir Titov and Gennady Strakalov were in the Soyuz capsule, and they had a launch pad fire. And this was a very interesting one because they had multiple means to try to initiate a launch abort system, and all of them failed except for the one commanded by Mission Control, and it took a while for that to finally happen. And what you're going to see here is this is a video. This is a shot from Mission Control. The Russian generals are watching it. They see this thing go off. They think that's the vehicle. It's the launch escape system firing. Here's the video. And the fire is consuming, there's a fuel leak, the fire is consuming the launch pad. They realize something is very amiss. The onboard detection system, the emergency detection system, failed to trigger because the wires burned. So they had to do a command-initiated abort sequence of the launch escape tower. Now you see the launch escape tower fire just as the fire consumes the vehicle. It is amazing footage. There goes the launch escape tower. Same system that's used on the Soyuz to this day. They're the Russian dignitaries watching it, and they don't realize that that's not the vehicle that's taken off. That's the launch escape system. Very robust system. There's a backup for a launch pad or early ascent abort, and that system has actually been tested. There was another, so that was in 83. In 1975, earlier on, they had a breakup during ascent, and this actually is footage of another one. I didn't have the actual footage. This was Soyuz 18. The launch escape system usually is jettisoned after first and second stage separation, just like on the Apollo capsule and on the Mercury capsule. So this was a staging separation problem between the second and third stage. The launch escape tower's already come off, so they don't have that means of escape. And what happened here was they had pyrotechnics that stuttered. They didn't separate adequately. The vehicle was carrying the second stage, and the third stage engine fired, and basically the whole thing started to tumble and break apart. But because of the robustness of the design, the capsule comes off, its descent systems, the drogue and pilot chutes activated and brought them down safely, actually right near China. And then to make matters worse, the vehicle lands on a mountain, and it starts rolling down the mountain, and actually almost went over a cliff when the parachute snagged a tree. So the point there is you're not safe till you're really safe home and safe, not just back on Earth. The U.S. program's had a number of failures as well on the launch pad. Many of these are not necessarily well known. Gemini 6 was a very interesting one. I have to do a whole talk on that because the crew, the Gemini Titan rocket fired and then shut down because of a plug came out and terminated it. And the crew met the criteria to eject out of it, but they didn't. And they were able to recock it and launch it a couple days later. This was a rendezvous between Gemini 6 and 7. There was a launch pad fire on one of the early shuttle flights. I actually have a little summary slide of that. There was an abort of a main engine failure. The U.S. space shuttle had 2 solid rocket motors that would fire for 2 minutes, and then they would fall away. And then the space shuttle main engines were liquid fuel, taking liquid oxygen, liquid hydrogen from that big solid, the big orange tank called the external tank, and they would burn for another 8.5 minutes. And there were 3 of those space shuttle main engines, and one of those failed, and they just did a burn for a little bit longer. There was also a center engine failure on Apollo 13 before the actual other problem developed. And then we've had a number of pad aborts where the liquid engines, the space shuttle main engines, fired 5 seconds before. They usually fire about 5 seconds before the solid rocket motors, and that they fired, but then there was a termination because of event sequence failures. So you had the liquid engines fire, and the solid engines didn't fire, which was what was supposed to happen. And there was a great quote by Steve Hawley on one of those aborts. He had a couple of these, and he said, "Boy, I thought we'd be a lot higher at main engine cutoff." It's a great saying. This was the launch pad fire that raised a lot of concern. This is the 12th shuttle flight. They had a liquid hydrogen fire, which is liquid hydrogen burns. Hydrogen burns, it's very hard to see, so they could tell by thermal readings, but they ended up having to put infrared cameras on there afterwards because the regular cameras didn't see the fire, but they fired the water suppression system, but this fire burned for 12 minutes. Now, the crew had an option, and there was a lot of discussion in the mission control crew arena as to whether they would do a pad abort. There are 4 abort modes that they could do. A mode 4 would have been where they get out and go down the slide wires and escape, and they decided we're going to stay inside the vehicle. Unfortunately, that was the right decision, but it could have ended up really bad. 1986, late January, very cold launch day, Challenger accident occurred. Most of us who are my age remember that, but for you guys that are, born in the 80s or 90s, you don't remember a Challenger, but it was a huge issue for the whole nation. And what happened here was the cold temperatures caused the O-rings that were used to seal the solid rocket motor joints together were cold, and they didn't have the normal resiliency. And so what happened is those O-rings leaked and caused a burn-through of one of the solid rocket motors. The burn-through caused the strut that held the solid rocket motor to fail structurally, and then it tipped over into the external tank. And what you see here is often erroneously called the shuttle exploded. It didn't explode. It had an aerodynamic breakup, and what you see there is the expelled liquid oxygen and hydrogen vaporizing, but it never actually exploded in a true chemical sense. What happened here is that the cameras are tracking it after launch, and this video footage was later available for analysis, but that is the crew cabin, the forward fuselage, and the pressure vessel that the crew are in. It broke apart, and the evaluation of that, by magnifying it, showed there's the nose cone of the shuttle, there's the forward fuselage with the pressure vessel that the crew are in, and they're still alive. They're unconscious as they started to lose pressure. They didn't have a protective system other than a smoke hood, which was like a motorcycle helmet that fed air, not oxygen, into it. And then eventually the capsule attained a downward aerodynamic velocity because of the trailing wires and the relative aerodynamic component of that. The crew was alive but unconscious until they hit the ground. The vehicle broke apart at a very low altitude, 45,000 feet. Commercial airliners fly that high, 60,000 feet. U-2s, SR-71s, and spacecraft launch up at that height. So it wasn't an unsurvivable if you had the right equipment, particularly pressure oxygen, maybe even a pressure suit. The crew survived the breakup. We know that from the autopsies. And the other thing is that several of the air packs that were found showed that they had been activated. So the crew recognized they were in a bad situation and they survived and activated it, but because they were only getting unpressurized air, not pressurized oxygen, they went unconscious, and then they succumbed to the impact forces on hitting the water. I don't know if I'll have time to go through this one, but this was another mission that was, it never resulted in a fatality, but it was this close. This was the Chandra X-ray Observatory, launched on Columbia in 1999. This was Eileen Collins' mission as a commander. And I'll play the audio from Mission Control because it is so overwhelmingly abnormal.
Start, 0. We have booster ignition and liftoff of Columbia, reaching new heights for women in X-ray astronomy.
So they have a fuel cell problem right off the bat. That's not good. They're what power the vehicle.
Columbia, Houston, we'd like AC bus sensors off. We're evaluating the fuel cell.
That's Scott Altman, who was the Capcom in Mission Control, talking to Eileen Collins.
Roger that, Columbia. Looks like we had a transient on AC1.
That's a electrical spike on the...
Columbia is now headed downrange, altitude 3.8 miles. And as we hear, all systems okay. It looks like a sensor on board.
I love PAO guys.
Engines throttling down.
The masters of understatement.
Columbia, Houston, we are critical to AC2 on the center engine, AC3 on the right. We've lost DCU-A on the center and DCU-B on the right.
Those are the control systems for the gimbals that control the main engines. That was it, So what happened here is they were having multiple problems. They had a fuel cell problem. They had control systems that were controlling the gimbals and the main engines that were reaching a critical limit. And what happened is they had two independent failures that occurred that were conspiring to stop this vehicle in flight. One was the multiple shorts that had occurred from servicing problems of the vehicle and short circuits that were affecting the fuel cell, and the other was that they had an under thrust from one of the engines because of a foreign object debris that had torn a hole in the engine bell. The other problem they had was that they had to have a waiver to carry a payload that would not have allowed them to land with the payload. Now, ordinarily, you launch, even when you fly a vehicle, say you fly a long-haul 747 or A380 to Australia, when you take off, after you take off, you can't land with that weight. You have to dump fuel for 2 or 3 hours before you can actually land again. So this vehicle had a waiver because it could not land with the weight it carried. Ordinarily, the Chandra would be pitched out at payload altitude, and they would be able to land the shuttle normally, but if they had an abort called a return to launch site abort, they had too much weight to land. John Young said, we never could land this thing, it would have torn the wings off because the wing loading was too high. So we had 2 failures on ascent that were conspiring to bring it down. One was the loss of thrust, and the other was the control of the gimbals. And they had a payload that would not have allowed them to do a return to launch site. And here is the debris has torn a hole in the center engine. You can see a streak coming out of it. Here's a view of it during ascent, and then the post-flight analysis showed this hole in the cooling vanes of the engine, where a piece of a plug came out and tore up the engine during the turbulent launch phase. That's why they pay so much attention to FOD. Even a little piece of anything out there can tear a hole in that engine bell. So that was one of those things that we missed it by this much. If those engines had shut down because they lost control of the gimbals that controlled their direction, the engines would have shut down, and the only option they would have had was to do an abort return to launch site, and they couldn't because they were overweight. Here's just a quickie one on in the commercial sector. This was during one of the qualifying flights for the X Prize on Spaceship One. And I'll show you the video. There's a lot of human factors involved in this, and they're working to try to rectify this. But what you see here in this video, you have the captive carry in the mothership. They're dropped off about 45,000 feet. The boost phase occurs when the butyl rubber nitrous oxide engine fires. And what happened here was a multitude of things. They had asymmetric thrust because of the ablative nozzle burn, and also because of unloading of the stick. And so what happened is this vehicle goes into an uncommanded roll of about 30 RPM. And you could see in the video inside there, even though that's a roll you could do in an acrobatic aircraft, inside that vehicle you're tumbling around and it's very disorienting. So that was one that we learned a lot from, but nothing bad happened. We've also had a number of other scenarios where we lost vehicle control. I won't go through all of these. Some of these are mechanical failures, and some of these are purely human related. I'll talk about the Gemini 8 was a mission that Neil Armstrong in particular shown like he did a great job in adapting to the situation and recovering it, and some of that may have contributed to him being selected as the first person to walk on the moon. This was going to launch and rendezvous with an Agena target vehicle. The rendezvous and docking was a big part of the Gemini program. What happened is the vehicle docks successfully with the Agena target vehicle. In fact, you can see this is a view from the Gemini looking at the Agena target vehicle, and they come up and back into the rear end of this. They dock successfully, and then during that time, a very slow, almost imperceptible roll started. At first they thought the Agena's got a thruster that's leaking and it's firing. The roll got worse, slowly got worse and worse. You can see over a period of between the time they docked and the roll was about a half an hour, and then after 15 minutes they did an emergency undock, and now the roll really went bad. Why is that? Because the problem was not on the Agena target vehicle, it was on the Gemini capsule. So this thing starts to roll at about 50 RPM. This is now getting to the point where the G-forces with headward and feetward fluid shifts is causing a serious cardiovascular compromise problem so that the person may not be able to respond, and more importantly, it's very disorienting. So you can't even touch a switch because the tumbling action is so great that you don't have good sensory motor control. And this is a plot of the actual RPM rate. You can see here, this is 300 degrees a second, or about 50 RPM. That's pretty fast. I mean, that would, if you did that in a free fall during a parachute jump, you would be very uncomfortable. So what happened was, they just started pulling circuit breakers and shutting everything down. And fortunately, they had training in this. It shows the importance of training, but they had done one of those tumbling trainers, multi-axis trainers, where they had to do certain things. And what they realized is, we don't know what's wrong, so we're just going to shut down everything. When they did that, they got the roll, they shut the thruster down, and they were able to they had to do an emergency landing in the Pacific. Interesting thing was, the reason that this failure occurred was that the thruster failed on instead of off. What was the lesson learned there? That you want to fail to the safe mode, and a thruster failing on is not as safe as a thruster failing off. So virtually everything that happens in space, there's some lesson that's learned that propagates and continues forever on afterwards. You wouldn't think, who would have thought building and designing something where a thruster would fail on would be a good idea, but it happened. This is another one of those cases where it's not very well known, but it's a very poignant example of the human errors. And this was during the Apollo 10, the final checkout of the lunar module around the moon before the landing a couple of months later. Gene Cernan and Tom Stafford are in the lunar module. They're going to go down to 10, I think it was 40,000 feet. They didn't give them enough fuel to come back because they didn't want them to land. So they actually, they didn't adequately fuel the tank, so they couldn't, if they landed on the moon, they couldn't have left. Anyway, this is the summary of that. Descent, this is after the descent module is going to be separated. The descent module is what lands, and then the ascent module takes it off the moon. So they're going to go, and they tested this whole thing out. And the lunar module was called Snoopy. Gene Cernan goes, okay, you ready? We're going to do the separation. They do this, they get ready to do the separation, and then the vehicle starts this uncommanded maneuver. Now, I went back through the transcript, and Gene Cernan said son of a bitch throughout the whole mission, so it wasn't just because of this. He's a Navy pilot like I was, and we do cost a lot. But anyway, the vehicle starts to do this uncommanded maneuver, and they have no idea what's going on there. And so they're trying to figure out why this thing has some kind of runaway thruster on it. And what it turns out, I won't go through this in too much detail, but this was a test of the Apollo guidance system. Who is it? Any MIT grads here? MIT, the Draper, Charles Stark Draper Lab, now Draper Lab, was the group that built the Apollo guidance computer, and it is an amazing piece of technology, especially for its time. But they were testing two systems out. They had the primary guidance and navigation system and the abort guidance system. And this is the Apollo guidance computer, and right here is the primary guidance and navigation system and the abort guidance and navigation system. And there's three positions for the switches. There's auto, attitude hold, and there's off, the down position, attitude hold, the middle position, and up is auto. And they had been used to using the primary guidance system switch, and so they had routinely would put that in auto. But now they were testing the abort guidance switch, and they were supposed to have it in the attitude hold, the middle detent, okay? And if you look at those switches, there's a little bit of a pull up, but not as much as you perhaps would like, where you really realize it's two actions. And so what happened is, from what I understand in the analysis of it, one guy puts it in attitude hold, and the other guy puts it in the next, he thinks he's putting it in attitude hold, but he moves it from attitude hold to auto. So they're in abort guidance mode. One guy puts it to attitude hold, which is where it's supposed to be. The other guy reaches down and he puts it in the position he thinks it's in. And one moves it from off to attitude hold. The other guy moves it from attitude hold to auto. When it goes into auto, now it's saying return to mothership. Where's the command module? That's what that maneuver in auto was supposed to do. But the command module is not where it's supposed to be. So this thing starts to fire and move all around trying to find the mothership. And it took a while for them to finally figure out, hey man, we had it in the wrong switch position. So that's another example of switchology and human factors errors that can plague us. Now I won't pick only on the crew, the flight crew, but we also have times where mission control, which is where I used to work, can also contribute to the problem. This was early in the shuttle program, STS-32. The flight controllers who were under contract, they weren't NASA, a lot of the positions were not NASA, they were contract, and they had to work longer hours and they didn't have the same kind of constraints that the NASA flight controllers had. This guy was working 12-hour shifts, multiple days, and he was dog tired. What happened? He had, in this scenario, you try to offload the crew. Any of you flight controllers? Okay, so you know how much training you get and all this stuff, but the flight controller's job is to try to limit the amount of crew activities by doing stuff on the ground. So every day for the shuttle, they would have to correct the state vector. The inertial measurement units would get a bias error, and then you would put a correction factor in there to reset the inertial measurement units. You could do that by having the crew do the optical sight of a star. You could have flight controllers do it by the correction factor, and so always the option is to have the flight controllers do it, not the crew. So what happened is the flight controller is uplinking a corrected state vector that is erroneous. The computer says this is out of limits and rejects it. You know, it's a positive sign where it's supposed to be negative or whatever, and so the computer rejects it. The flight controller goes to his damn computer, and he continually tries to override it, and the computer keeps rejecting it. Finally, he figures out, he puts all his effort into figuring out how to override the computer's inhibits. He uplinks the state vector, which is erroneous. Now the shuttle goes into what's called an LOS period, loss of signal. The crew's asleep, they're in an LOS period, and the computer input to the guidance system now starts to saying, hey, I'm not where I'm supposed to be, and it starts firing thrusters. So now it's in loss of signal, the crew's asleep, and they can't command it to go back to where it was. So for the 10 minutes or so that the LOS period had occurred, the crew's asleep, and the vehicle is just tumbling on its own, firing its thrusters because of a human error. Great lesson learned. After this, there was a massive effort that went into circadian shifting and understanding sleep, and there's still flight controller studies ongoing to better improve the sleep quality for flight controllers. This is a great example of human factors error. This was another wonderful study in human factors. There's a great article here. If you want, I can email you a copy of it. This was the progress mirror collision that occurred in the 97 time frame. Actually, there were two of these events. The M233 was a near miss, and M234 was a hit. So they had already tried this maneuver once and almost hit the Mir space station. But because of mission control in Russia said, you got to keep trying this, you're going to do this again. What was the driver? One was to save money. Instead of using an automated docking system, they decided we could save money by reducing our bandwidth and our dependence on the Ukraine's KURS system. So we're going to go with a manual control system. The crew have to do this manual control. It's like flying an unmanned aerial vehicle, where you're in one vehicle, but you're flying it as with the visual imagery from another vehicle. And there were a whole series of human factors. They slam shifted the crew, they didn't have adequate sleep, they weren't well trained in it, over and over and over and over again. These things were warnings to the crew. The other thing is that you want to know where the vehicle is, how far away it is, and what's its closure rate. So you want to know distance and rate of closure. That's a kind of standard thing for rendezvous and docking. But because they thought the radar from the range rate system was jamming the video signal because the video signal was dropping in and out, they said, well, shut down the range radar. So now all they have is the visual rate. And what happens is, that was the collision with the Spectre solar array. Here's an actual video of it. This is a video from BBC called Mere Mortals. It has Mike Full talking about it. And this is a camera that's actually on the display in the mirror, and the mirror is buried down in the clouds. I don't know if you can hear any of this, but he's basically saying, I couldn't see where the vehicle was, I didn't have the range rate closure, and they never did really get a good handle of where the mirror was. One of the things that the US side learned was when you're doing rendezvous and docking like that is instead of having the vehicle that you're coming into being against the Earth where it's harder to see, is you have the vehicle out in space, so that's the only animate object out there. So that was one of the lessons learned there. We'll talk a little bit about environmental effects. You know, we talked about space vehicle effects. We've had a whole bunch of combustion events, a euphemism for fires, mostly avionics systems. On Soyuz, which is the early Russian space station program, Mir, Space Shuttle, and ISS. A lot of toxic environmental factors, including high carbon monoxide as a combustion event, toxic products, and I'll talk a little bit about some of these later. And we've also had water contamination. So a lot of these issues from...
And that took about 2 days.
This is Andy Thomas, who was
Manifested symptoms.
one of the last guys on Mir space station talking about one of the fires.
Those levels, you have nausea, a certain amount of confusion, invariably a headache because you're oxygen deprived. It's just a very uncomfortable feeling.
So one of the issues with that was that it was a low temperature catalytic oxidizer that had had a fire, and they analyzed it and think it was because the thing was configured wrong by the crew. So, you know, you can see human errors, you know, embedded throughout all these kinds of events, and this is one of those examples. So we saw it with the Mir Progress collision, we saw it with this system, and then the previous slide showed Jerry Leninger, who was on board when the solid fuel oxygen generator ruptured its canister and almost burned through the hull. This is one that, another human error, and I'm not trying to pick on humans, but you know, any of you who are human factors engineers, you know that about 70% of mishaps have a human factors component, and that's not at all unusual when we look at these. In fact, if you went through this list and really dug deep in it, you would probably find human factors errors of at least 70% of this list as well. So that would be a great, you know, project or thesis. Apollo-Soyuz test project. After the separation from the Soyuz, the Apollo capsule is coming down. It's got Vance Brand, Deke Slayton, and Tom Stafford. There's Deke Slayton, who was the head of the astronaut office, Vance Brand and Tom Stafford in the middle. So they're coming down, and they're following the vehicle systems like they always do. And this is always the battle you have between automated systems and manual systems. How you follow it and what's going on. What is the thing doing what I want it to do? These guys are getting antsy. The normal landing system, which follows a very precise sequence of events. This comes after this, and after this, and after this, and it occurs during an exact time during the altitude and velocity regime of the capsule coming in. They're coming down, and the crew's going, I don't know about this. I wonder if this thing is working right. It may be that they want to fly the vehicle because they're pilots, or it may be that they've misinterpreted some of the cues, like where they are in the altitude velocity regime of the reentry capsule, but they decide, I don't like this, we're taking it out of auto. We are turning off the auto landing mode of the capsule. And they're going to go to manual mode. What does that mean? It means they now have to follow that precise sequence of switch throws at the right time, and they miss one. And what happens is the capsule is coming down, the capsule equalization port has been opened. At the same time, the thrusters are firing to try to dampen the capsule's motion under canopy because they did not follow the sequence. Now, that happens because of a variety of reasons. You know, you miss one little teeny line, and any of you ever written flight rule checklists? You know, you look at those things, and if you didn't know exactly what they meant, it would be hard for you to follow them. But you take somebody who's been in space, they may have a little bit of the space stupids, they may have a little bit of motion sickness or whatever, but they don't follow that checklist in the precise manner, and what happens is a thruster is firing while the vehicle is open to the atmosphere. And that toxic fume, the nitrogen tetroxide, gets inside for just a short period of time. And after a while, they realized, man, you know, there's something wrong here, and they shut it off. But by that time, the capsule has already filled with enough of this very toxic material that they've already suffered a sequela from it. Then, to make matters worse, the capsule lands in the water and goes into the inverted position with the nose cone down, the heat shield up, and now they're hanging from the straps. Their personal protective equipment is above them now. They have to unstrap, they fall out, they have to climb back up and get the capsule, get the personal protective equipment. One guy, Vance Brand, goes unconscious. Tom Stafford finally gets free, gets the masks and puts them on everybody, and the capsule eventually flips over. And Hector, you've done toxicology analysis. You guys have looked at this case, I'm sure. Oh, really? Well, it's a good one to look at. But anyway, these guys suffered a very, very severe chemical pneumonia, pneumonitis, from the nitrogen tetroxide exposure, and were hospitalized in the ICU at Tripler Tripler Medical Center in Hawaii for 2 weeks because somebody didn't follow the checklist. So the importance of human factors in checklists, and when you decide to override an automated system that has been vetted, you better make sure that everybody follows the right procedure. And then this just shows you the permissible exposure limits, were far exceeded the acceptable levels of standards, and they were lucky that they got to them quickly and were able to treat them with intensive critical care medicine. This is just a quick list. I won't go into any detail because most of you are not medical types, but what this shows you is all the different kinds of medical conditions that have occurred in active U.S. astronauts, not in space, but here on the ground. Now, this is despite a robust, extensive surveillance and screening program. I mean, literally, any of you have ever been through an astronaut selection? I mean, it's, what do they say, tubes and something in every orifice. They scan you, they probe you. You look at the movie The Right Stuff. It's like that, except worse. So these are medical conditions that would kill you if you didn't have access to intensive medical care. Pancreatitis, gastritis, duodenal ulcer, urinary kidney stones, 14 kidney stones in 10 astronauts. I mean, you name it, retinal detachment. Wow, you look at that list, and these are in healthy, screened astronauts. We're really lucky that stuff hasn't happened in space, but oh, it has. And the only reason that we haven't had them in the US program is the majority of long-duration missions where you're going to be in a longer risk period of duration exposure has been in the Russian program. And so they've had 3 times where they actually abandoned the space station for medical problems, and they had 3 other times where they were in the process of abandoning the space station when the problem spontaneously resolved. I'll go through these just to point out the concerns that we have, particularly on the medical side, about getting people off the space station. So we had a Soyuz 5, they had a combustion event and severe headaches. The crew said, we don't want to stay here any longer. And there was a battle, and they decided to come home a few days early. That same thing happened on the NASA Mir program with Andy Thomas, but the crew sucked it up, didn't get oxygen, and have some health effects as a result of that. There was another mission in the Soyuz series just before Mir where a crew member got a urinary infection. Men don't get urinary infections for the most part, but try to pee when you're on your back, which we had to do in medical school on the bedpan. You know, it doesn't work. The gravity helps, you know, and when you try to pee on your back, which is what it would be like in space, what happens is you don't empty your bladder. And when you don't empty your bladder, you end up with a potential for urinary infection. So guys do not get urinary infections except when they have to pee on when they're lying on their back. And the third case was a case of a severe ventricular arrhythmia, which you can actually see on this, that occurred, that was another early mission termination. And then these are the three cases that were close calls. One was a dental abscess. The Russian dentition has always been an issue. Now we do a lot of prophylactic work on dental problems. This is a fascinating one too. This is the one where in the later stages of the Mir program, the ethylene glycol, which is the primary coolant system, would leak and it would form, it would collect. And what happens in space, it doesn't pool on the floor, it forms balls because of surface tension. So the commander, Dezhurov, was going through an unlit module in Mir, you know, really cool, it goes through the unlit module, his head goes into a ball of ethylene glycol. And now his head is like a fishbowl with ethylene glycol. It covers his face, it burns him real bad, and it gets in his mouth, and he starts getting severe respiratory compromise. And the only reason they didn't abandon the vehicle was that the US guy was Norm Thagard, who was a US physician. He says, hey guys, I don't even know if we're going to survive an evacuation. Let's treat him with steroids. And he was able to get this guy back in shape. And then the third case was acute abdomen. You know, this is when oh, my belly's killing me. You go into the hospital. They thought it was appendicitis. It turned out to be a kidney stone, and that passed, and they were able to avoid evacuating for that. I'll talk a little bit on the psychological environment. Anybody with a behavioral health or psychology background? This is awesome stuff because nobody ever knows about all this stuff that's happened. It's amazing. This is Valery Polyakov, who spent 14 months on Mir, and he spent 5 hours a day exercising, and he spent the rest of the time looking at Mother Earth because it was so important to have that connection with Earth. Now, what's going to happen when you go to the moon? The Earth is the size of your thumb at arm's length. It's still a pretty blue marble, but now you go to Mars, it's a pencil dot. It's no longer a pretty marble. It's no longer this beautiful vista. So the psychological components are one of the top 3 risks that we think are going to face us for long-duration missions. This was photos in Valerie's sleep station of this family. Now we have these really cool pictures that show up randomly on each crew member's screen that shows them various, you know, surprise photos on their laptop as screensavers, and that's a huge psychological boost. But you can't even comprehend what this is going to be like when you go to Mars and you can't abort to Earth. You're at least 6 to 8 months away, depending on where you are in the cycle. These are a list of all the events that have happened from a behavioral health standpoint. I won't talk too much about this. 1985, payload specialist Tracy Wang goes crazy because his payload fails. I have a whole talk on that. Dezhurov, who is the same guy whose head went in the ethylene glycol ball, his mother died. Mission Control says, I don't think we should tell him. You know, we spend a lot of effort with our crew now saying, when do you want to know about something bad? You know, do you want to know about the dog, your wife, your kids? And they decide, I want to know right away. I want to know, after things are settled down. We're not in a high crisis ops. But you don't hide things from people unless you've talked about it ahead of time. When he finally found out he went into an acute withdrawal reaction, I've got great videos of these things. Homicidal, suicidal, mutiny. There was the Skylab 4 mutiny. There was the Apollo 7 mutiny. There's the Jerry Leninger on Mir 5 mutiny. I mean, there was tons of these things. Fights, you name it. I won't go through Taylor Wang's case. That's a fascinating story in itself, and is why they started to put locks on the hatch, because they were worried he was going to blow the hatch. And afterwards, they quit the payload specialist flying for quite a while. This is a topic from Shannon Lucid. Even if the space station has the latest futuristic technology, if the crew members do not enjoy working together, the flight will be a miserable experience. Sasha Lazutkin, this was after the Mir Progress collision. He disconnects the wrong cable, and the whole power system for Mir shuts down. They can't get the escape modules to work because of that. I mean, the thing. I mean, there was and that was probably a fatigue event. And then here,
The Russians know only.
This is a tape of Valentin Lebedev, who wrote Diary of a Cosmonaut, and this is a briefing by one of his psychologists.
The Russians know only too well that pairing the wrong crew members could lead to tragedy. In 1982, Russian cosmonaut Valentin Lebedev sent a message to Mission Control.
If you don't bring us down to Earth now, I'm not going to work with this corpse anymore.
After 6 months in space, Lebedev was prepared to kill his fellow cosmonaut.
And
Russian Mission Control talked him out of what could have been the first murder in Earth orbit.
And I have an opportunity, because a lot of my friends are astronauts, in talking about it, and I can tell you that there are times when they really do want to kill their crew members, especially the ones that eat their food or get, no, I'm serious. And it's interesting, but the CO2 levels are now implicated as a factor in increasing irritability in crew members. Okay, so that was Valentin Lebedev. He wrote this great book, Diary of a Cosmonaut. Here's Sasha Lazutkin.
In the station, in escape pods.
So this is after the Progress has collided with the Mir.
He had already decided to kill himself.
One of the cosmonauts, actually, Lazutkin, told me that on the 10th day, he decided to commit suicide because he couldn't stand it already. He went to a remote place in one of the modules, and before suicide, he decided to sleep.
The cosmonaut woke up and chose to live.
So, I mean, these are things that even in the psychology behavioral health group, they don't always recognize these things as happening.
It happened in 1973.
This is the Skylab 4.
Too many orders from the ground, and the crew went on strike. It was a serious breakdown of command and control. A similar strike happened on the Russian Mir station.
So, and these are well documented. This was Skylab 4. Jerry Carr talks about it. You know, it was basically too much work, not enough time to deal with it. And what we learned when we went back to long duration missions was that we would give the crew a job jar and they would decide what order to do things. We would give them more control, more autonomy. But during Skylab 4, which was the 84-day mission, they were pushing and working the crew, and they finally had enough of it. A similar thing happened on Apollo 7. That's well documented in various books that astronauts read. In fact, it's cool. If you're really interested in this, get every book that any astronaut's read, and you can scour it for unbelievably cool stories like this. This is Jerry Leninger.
Cut off and stuck with myself that I felt during that time, and also how vulnerable I was. And I saw in my crewmates some pretty serious psychological problems developing, people kind of going off the cliff and not able to function at the level I'm sure they wanted to function at.
Now, Jerry Leninger also mutinied. He refused to communicate with Mission Control for several weeks because he was always the one that got the crummy comm pass. So he wanted to talk to his wife and his kids, and the Russians kept the good, comm, that wasn't ratty or, a lot of static. And so finally Jerry says, if you're not giving me time to talk to my family, I'm not going to talk to you guys. And he just shut up for 3 weeks. Anyway, post-flight, we all know about poor Lisa Nowak. We've had suicide and suicide attempt in astronauts. We've had interpersonal conflicts, behavioral change, substance abuse, you name it. And these are people that are obviously very well screened and psychologically, in the best of shape. God knows what's going to happen when we start seeing, non-professional astronauts fly. In fact, when the latest study was done on the Virgin Galactic group, just getting in the capsule to do a centrifuge run freaked a lot, over half of them out. That's a picture of a solar eclipse taken from Mir. I'm going to have to really go through here because I know Janice wants me to finish up here. But
No, take your time, seriously. Like I said, but they're not on the schedule. After the 2 hours, they're allowed to leave, but they can stay.
we don't fly the shuttle anymore, but the shuttle was one of those vehicles that required crew inputs. The crew flew the vehicle. Once it got below Mach 1, around 100,000 feet, the crew would start flying the vehicles, and they would actually land the vehicles. And what I did when I was involved in the shuttle program was we were trying to fly the shuttle for 30 days. It was called the Long Duration Orbiter Mission. The Extended Duration Orbiter Mission was up to almost 18 days. But what you see here are two parameters that are essential for landing a vehicle. Every time you fly an aircraft and you know that pilot just knocked my fillings out, you know, that sucked, you know, because you hit too hard, you know, that's bad. And it's bad for vehicles because it, you know, can shear the landing gear off. So the vehicle has two parameters that are primarily important on touchdown. One is how fast it touches down, the landing speed on touchdown. You think, hey, that's pretty easy to do, except you don't have an engine. So you can go, you know, you have to control it by a speed brake and your aircraft and the angle of attack. So ordinarily, you want to target about 205 to 200 knots, plus or minus a little bit, depending on the vehicle landing weight. Now what you see here is, this is 200 knots right here. That's where they should be landing. That's the, you know, flight rule limit, 214 knots, and that's the 225 is the red limit. That's the landing gear shearing off factor. And then too slow. Who are pilots here? Any pilots? Well, you don't like to fly too slow. Why? Because you stall the vehicle and it slams down too hard, and that creates the second issue, which is the vertical velocity at touchdown. Look at the variability here. These are all test pilots, most of them military test pilots. They've had to have 1,000 shuttle training aircraft dives before they can fleet up as commander. This is appalling performance. It is. 160 knots? Wow. That's below shuttle, you know, stall speed. And above 225, that's the shear landing gear limit off. And it's also related to duration. So longer the crew's up, the faster they touch down, and also the harder they hit. So we know, what is this? It's not crew performance, it's a neurovestibular effect on crew. And it's something that we really were concerned about. If we went to a 30-day mission and that graph continued to go up like this over here, now, you know, the average is going to be around 225, which is the landing gear limit. So we were really concerned, and we actually ultimately decided not to do a 30-day mission, although the vehicle was rated for it. Vertical velocity at touchdown. You know, you're sitting there, you have your drink in your hand, you know, and you hit down, and you know, as a Navy guy, we would land very hard because that's how you do it on a carrier. And so Navy pilots typically really smack it down. They want to know that they got that vehicle down because they don't have but a couple hundred feet to land in. So ordinarily, the shuttle would not touch down faster than 3 feet per second. Okay, nice greased on landing. Look at these. This is the flight rule limit, 3 feet per second. That 4.5 feet per second is the, you know, a shear limit. Look at how many, I mean, it's not a lot, but it's still, these are test pilots. 2 out of 100 pilots exceeded the structural limit. We had a blown tire, and we had, one of these missions, it was a very long mission. If the vehicle had any side load, crosswind load, it would have sheared the landing gear off. We were really lucky. Same thing goes, high speed on touchdown, high vertical velocity on touchdown is correlated with duration. I won't talk too much about spacewalks, although I got 2 hours to talk on this. I'll just go through this real quick. Huge variability. These are two military aviators, Nancy Curry on the left, or on your right, and Scott Altman, Navy aviator, 6'4", 240 pounds, 5'2", 110 pounds. Those are military aviators, and that's a limit now. We're going to go to 1 to 99 percentile, and it's got huge ramifications for human factors. Huge number of things have happened in space. I'll just go through these real quick. Look at all these. EVAs resulting in injury, shoulder problems, EVAs terminated because of crew injuries or cut gloves. We've had several cut gloves. I'll show you some of the problems with that. 40 tool releases. 40! That's a huge number. Those things are, you know, cameras, some of these tools cost millions of dollars. Huge number of, why do EVA highly trained astronauts drop tools?
An hour and a half into the mission, cosmonaut Alexei Leonov floats out of the spacecraft through an inflatable airlock, becoming the first person to walk in space. Leonov stays outside the spacecraft for 12 minutes, but when he tries to re-enter the airlock, he has trouble getting back in because his suit has ballooned. He is forced to deflate the pressure of his suit just enough for him to bend the joints and get back inside.
Now, that was the first spacewalk, and obviously they learned a lot. Anybody EVA engineers, EVA guys? You know, so you guys probably learned all this. You know, the Russians have 2 settings on their regulators so they can go to an emergency depress lower. This is, I've got a couple of videos of EVA crew dropping tools, or I guess releasing, there goes the tool bag. That's, or the camera. That was a camera that went off in the distance. And then here's Heidi, Steffenshire Piper, who drops the whole tool bag. She's a Navy diver, so she's used to, and it's like, God. So she's not alone here. People say, oh, you know, women, that's bull, because the majority of tools have been lost by men. But why do experienced crew members lose tools? You know? I mean, it's a perplexing factor. It might be, you know, they're rushed, they forget to tether, but these are consequences. And if they don't tether themselves, which has happened on one Russian mission, and the crew member was floating off and the other guy grabbed him, you know, they would be lost in space.
I'll tell you, that spacewalk, the whole time it felt like I was falling from the edge of a cliff, and not only falling from the cliff, but the cliff itself, being the space station, was falling the whole time. And so it was a remarkable feeling, and you had to keep yourself under control and talk yourself into saying it's okay to be falling, and seeing the spectacular view of the Earth and the big space station sprawling.
That was Jerry Leninger, who was the first U.S. guy that was called and did an EVA in an Orlan spacesuit. And what he brought up was this thing about falling, you know, which is not like fear of falling, but it's just this falling sense. It has affected U.S. crew members that have to transit out on the arm. And I've had them tell me they had to curl their toes as tight as they could just so they knew they were actually touching structure. The Russian Strela crane has a moment to it. It's like a telescoping thing, and it's not super stable, and crew members would feel like they're falling. And in the U.S. airlock, when they would open it up, it would be the Earth underneath them, and crew members sometimes would get stuck going out because it's like a first-time skydiver, you know, not wanting to get out of the planes, you know. So they learn, don't go out head first, go out feet first, so you know you're already halfway out. But there's, you know, it's not a huge issue, but it's certainly an issue. And if you go back to this picture here, you know, and you look at that picture there, payload bay transit out to a work site, and the Earth's down here, you can bet that guy's holding on for dear life, even though he doesn't have to. Anyway, all right, so where are we here? I want to get finished up here. Oh, here's a cool one. This is a fatigue event. You know, the crew ordinarily they don't take their boots off, but they took these off and they put them on backwards. Any of you skiers, can you imagine skiing for 6 hours with your boots on the wrong boots? Ow! A lot of the MMOD, I won't talk too much about it, but that's, you know, becoming more and more of a problem. And those kinds of handrail hits, you know, you see that snagged there, and that can certainly tear a glove and cause problems. Gosh, I'm so far behind, Janet. I'm going to just go through this real quick. The first U.S. space fatality was the X-15 mishap that occurred towards the end of the X-15 program. And I bring that up because it has a lot of relevance to the suborbital community now, who are going to be doing, you know, captive carry, air-launched, winged reentry vehicles. This was Mike Adams. He was an experienced Air Force test pilot, his third flight in the X-15. And he's doing a payload that has some problems. He gets distracted. The vehicle starts to turn sideways during the coast. You know, you have the boost phase where your engines are firing. Then you have your coast phase where you're in microgravity, and you're basically not aerodynamic, and the vehicle starts to turn. He's working this payload problem. He's not paying attention that the vehicle is turned sideways. He also didn't reset his attitude indicator from the payload, which was primarily to focus on roll, to heading, which is what he needed to have configured during reentry. So he comes out of the coast phase and starts picking up aerodynamic forces, and by this time he's, like almost 90 degrees to the velocity vector. One side gets lift and the other side doesn't, and the vehicle goes into a Mach 5 flat spin and eventually breaks up. It has to do with payload distracting him, the fact that he didn't configure his attitude indicator from the payload operation to the reentry operation, a lot of human factors there. I even have a video of the breakup, but I'll go through that quickly. Anyway, and that he was awarded his astronaut wings posthumously. Vehicle reentry issues have caused a lot of problems, particularly during configuration for the reentry phase. Early on in the Russian program, they used a ball or a sphere as their capsule, and the service module or consumables module would separate, so you reduce the landing weight. And a lot of times that separation would not be complete, and so this thing would fall down with it and cause the reentry to be very problematic. And this is an artist rendition of that. This is a shot from the space station of the Soyuz coming in. That's the descent module, and the orbital and service module are burning up, and there you see it burning up completely. The separation of these modules requires precise firing of pyrotechnics to separate the orbital module, where the crew can live in space, the descent module or crew module, which has the heat shield and the couches, and then the consumable module of the service module. The first one that came in off nominally was Soyuz 5. Basically, the orbital module came off, the descent module and the service module stayed together, and as you see in this picture right here. And so what happened is the center of gravity changed, and so now the vehicle, instead of coming in with the heat shield in the velocity vector, is coming in with the hatch in the velocity vector. So these separation concerns are very real. This was in 1969, early Soyuz program. Has it happened recently? Absolutely. This was TMA-11. This was Peggy Whitson's mission. Okay, Expedition 6. The service module did not separate from the descent module like it should have, and it came in backwards or forwards. It came in with the hatch and the velocity vector, and it burned the whole front end off. In fact, the crew surgeon told me, he said they were 10 seconds from penetration of the hatch. And this is the hatch, very badly scored, and also what's around here are two parachutes, which we're lucky that they didn't end up getting burned. That was one of the thruster packs that shows that the burn pattern. Here's the hatch, the shield, the heat shield's on the other end. I'll go through several of the fatalities. We had the Soyuz 11, we had the Challenger, and Soyuz 11 was a re-entry misconfiguration that resulted in a fatality. There were definitely human factors issues involved here, but what happened is the same thing happened. During the pyrotechnic stutters, the pyrotechnics are supposed to fire in a very precise sequence, like say 100 milliseconds apart, so there's not a jolt that goes through there. And apparently the pyrotechnics didn't fire in the right sequence on Soyuz 11, and so what happened is a equalization valve that opens down lower so you can get the hatch open, supposed to open at say 20,000 feet or so, it opened at 400,000 feet. And now the crew are inside and their capsule is depressurizing. It's about the size of a quarter, it's depressurizing slowly, they feel their ears pop, they know something's bad. They have to try to configure the valve to shut it. But it was a stem valve that took like 30 turns, and they got halfway through before they finally passed out from lack of oxygen. Now what went wrong here? They weren't wearing suits. And they weren't wearing suits because the Russian program office made a decision, we're going to fly to the space station. This was a Soyuz 1, the very first Russian space station mission, 22 days on orbit. They did a great job, but they could fly 2 crew with suits or 3 without. So they made a decision, let's don't fly them with suits. Let's fly more crew and have a longer record. So now we'll have, over 60 days of Russian, cosmonaut time. And unfortunately, they paid the price because during reentry, that stuttering occurred, causes the equalization valve to open. The crew knows, hey, we can shut that valve off. But they had one, they went to the wrong valve, and it took too long for them. Meanwhile, the cabin atmosphere is depleted, and they pass out from hypoxia and eventually died from exposure to vacuum, and actually we went and met with the Russians, talked about it, and got their autopsy information as part of the Columbia investigation. I talked to some of the crew recovery guys there. They said they all had pulses, but all they had available was basic life support, not advanced life support. When I was involved in the Red Bull Stratus project, we developed a treatment protocol for this exposure to vacuum that we could do in the field, and that's now the standard of care. Columbia, this shows the analysis of the breakup based on the flight data recorder that was recovered before the vehicle broke apart and the flight data recorder quit working. This is the attitude the vehicle was in. The crew definitely knew they were in a bad situation. The pilot started, as part of the loss of control recovery procedure, shut down the APUs and was restarting them when it got to this point here. 46 seconds they were alive and working the problem, and then at the end of that time, the crew module broke apart in almost identical fashion to the Challenger. At the same point, they start to depressurize. Now this time they're in a different position. They have the advanced crew escape suit, but not everybody had their suit in a configurable position. 2 had the helmet off, all of them had their visors up, and 3 didn't have their gloves on. So if you don't have your suit in a configurable position to survive, it isn't going to help you. And I've talked to a lot of the shuttle commanders, and probably about a third of them didn't wear their gloves because they didn't like the effect it had on the hand controllers. And so there were a lot of lessons learned from this. I know some of the crews after this, particularly Pam Melroy, who was the commander who was also involved on this team, made her crew go through training on making sure you put your visor down as soon as possible if you recognized an out-of-limit situation. This was a picture from an infrared camera taken from an Apache helicopter flying at Fort Hood, Texas. And this is the space shuttle main engines, and then several seconds later, D-21 was the crew module, and this breakup occurred, the final breakup was between 148 and 138,000 feet, probably Mach 12, but it was in an altitude regime, again, where we've seen, ability to potentially survive there. We had a lot of problems. The helmets were non-conformal, so they created some damage. It'd be like wearing a motorcycle helmet that didn't have any padding, so your head would just bounce around inside. The restraint systems didn't work because of the inertial reels, didn't lock up. There were a variety of crew support, life support system issues. I'll just briefly talk about landing. This was Apollo 15. One of those thrusters fired and cut the parachute riser. Soyuz 1 was the first Russian mishap in 1967. Vehicle was launched before it was ready. The crew knew that it wasn't going to be able to work right, but they were trying to launch on an anniversary like the Russians do, and they ended up having a big funeral as a result of that. I won't show the video. This is an interesting analysis of it. I went to Russia and spent a lot of time trying to figure out all these different mishaps. They were landing a capsule for the first time where the crew was going to be inside and not come out with ejection seats. And so they had a lot of problems with the descent systems. Any of you guys parachute engineers? So you probably know all about all this stuff. But what happened was they decided towards the end we needed a bigger parachute. So they had to pack a bigger parachute in a smaller container. And they actually, from the stories I heard, they were actually hammering the parachute to get it to fit inside the container, parachute container. The other problem they had was when they were doing their final closeout prep, they were going to spray an ablative thermal protection system, this kind of black asphalty looking stuff around the outside. They didn't put the hatchback on, they just cut a piece of plywood and sprayed the liner on, and it got inside here right around this lip. And so you had this really super tight packed parachute and then this friction material that leaked in when they were spraying that liner on. So when the parachute came out, it stuttered. It didn't deploy in the right sequence, and so it essentially did what's called a cigar roll, came out, and then it fouled with the reserve parachute, and then you saw the consequence of that. I won't go through too much. We've had a lot of problems with landings, bounces. This is a bounce, and you see how the vehicle comes down and bounces, you know, particularly in a high wind condition. This was also poor Peggy Whitson's flight. So she comes through upside down, and the crew recovery forces are, you know, because it's not in the area they're supposed to come down, they're flying in their helicopters, and this is what they see. No big orange parachute and a big fire. There's the capsule right there, right there. The parachute burned up. It didn't burn up because of the heat on anything. It burned up because some farmers were burning the field, and they just happened to land in the burning field. A lot of X-15. We had 2 X-15 mishaps. One because it was overweight on landing because they didn't dump enough fuel, and the other, the nose gear failed and it rolled. Here's a Spaceship One doing a ground loop. You don't hear about that. This is a great story because I always tell you it ain't over till it's over. You know, just because you're back on Earth doesn't mean squat. Okay, you could land down like the Soyuz 18 where it rolls down the mountain and almost goes off a cliff, or you can be like Soyuz 23 where they do an emergency undock and they land in this lake, and the crew recovery forces are trying to fly to them in this god-awful blizzard, and they can't get there, so they figured, well, we can't fly in this. It's just, you know, it's impossible. And they thought they had died. They actually were going out the next day after the storm abated, and they went out and thought they would find them dead, and they were actually alive. And they were very cold and pissed off. So it's not over till it's over. Quick summary. Spaceflight risk occurs throughout all the phases of flight, but it's primarily been launch, ascent, reentry, landing because of the energy transfers. Suborbital flight risk, about 1 in 200 based on the X-15 data. Capsule risk, about 1 in 60, 1 in 70, and about the same for a winged reentry orbital flight based on the shuttle program and the Soyuz. The hazards in the space environment include the hazards of spaceflight include the space environment, the vehicle environment, and the mission architecture. The fact is that you can see medical events that occur in even highly screened and selected crews. So you have to have a kind of a posture of how much are you going to be able to take care of them, do you bring them back or not? And obviously that's going to change if you're in deep space, where you might have a 20-minute one-way comm delay and no abort options. Our countermeasures, despite the very focused effort, they still don't have the full capability. It's basically like an ambulance plus. Human errors. Like everything in aviation, human errors still contribute to space mishaps, as we've shown in some of these examples. Here's my contact info. I'd welcome your queries, questions, thoughts. And I don't know if we have time for a few questions, but feel free to contact me. I think I left my business cards over there if you want to get a hold of me. Thanks a lot.
Great. I have a question. Are you working with HRP on the 1 year?
I'm working peripherally with them. Some of our scientists are, particularly doing the genetic studies. And I'm looking forward to that mission. That'll be. The Russians have, I think, 4 people that have flown on 1 year missions, and so we need to get more. We need to get some U.S. guys out there. Okay. Oh, that's sure.
Full disclosure, I actually support the FAA's Office of Commercial Space Transportation.
Oh, awesome.
So I'm more interested in your perspective on commercial activities. If you can elaborate on that, especially in light of the history that you just provided about government-run programs and obviously the problems that have arisen in that sector, and now looking at commercial companies that are looking to fly tourists.
I know. Well, I should give you my. So this is the 1,000 Ways to Die in Space. You know, you have to see my crew survival talk about, and I brief them on that. I talk about part of this goes into the informed consent prospect of it, but these are heavily funded government programs, and the U.S. and Russian side still had mishap rates equivalent to a bomber crew in World War II. Wow. What do you think commercial space is going to have to face? Everybody's talking, well, maybe 1 in 10,000. Boy, I wish. You know, we'll be lucky if it's 1 in 1,000, because right now it's about 1 in 100 is what we anticipate. But I'd be glad to work with you. I work with Ken Davidian and Melchior Antonaro, and you know, my feeling is the more we can share, the more they can learn from the U.S. programs, you know, that have spent 50 years, every lesson somehow written and learned the hard way, the better. The good news is a lot of the commercial space companies have former NASA people, NASA astronauts who can carry on that legacy. And I look at the launch failure rates from the early programs of the US and now with, say, Falcon 9, and I go, wow, I mean, we would lose, you know, a huge number of vehicles in early launch testing, and I'm shocked, not in a bad way, but I'm shocked that Elon Musk has been able to launch so successfully and make milestones. I think that shows the commercial space industry gets it. But I'd be happy to share anything I can with you all.
Can I ask one follow-up? The video that has been released of Felix's jump in his spin, is that comparable to somebody potentially passing out, or was that?
Oh, yeah, I could do a whole talk on Red Bull. I could show you the video if you want to see it. His spin, you know, the reason we did that program was to demonstrate that a human could penetrate the sound barrier in the upper atmosphere. Because when I was on the Columbia, you know, investigation part, there were a lot of guys that go, well, it wouldn't have mattered, they couldn't have survived, why bother? Well, that's not my approach. My approach is the kind of the Gene Kranz, you know, you never give up. Failure is not an option. You will do everything you can to bring the crew back alive. And what we had to do was to prove that you could survive that. He went into a spin right before he broke the sound barrier. If you want, you guys have time, I could show you the video. It's super cool. You want to see it? Okay. This is the technical video that we do not show this video outside of technical audiences. Now, and you guys can save all your questions for, okay, so this is the video. I do a 2-hour talk on this because it's about, we developed crew survival lessons learned from this, and I am so proud to say that as soon as this program ended, boom, another one started up. So we are already doing a follow-on to this program. What you're going to see here is a fused data system where we took 3 cameras, the head up on the chest pack, the head up on the right leg, and the head down on the left leg. Airspeed up to 900 miles an hour, altitude. This thing just goes around like a spinning top. This thing goes up to 850 miles an hour. This is the heads-up display, Mach and miles per hour, respiratory rate, heart rate, the altitude bar, you know, it's a bar, like, so you have altitude on one side and airspeed on the other. So that's at 127,000 feet. And then altitude versus time, G-force versus time. That's the opening shock. That's the landing, and that's the spin. And then this is the speed versus time with the 30 seconds in supersonic. The 3-axis accelerometer, and then this is the resultant G-vector. So here he's standing on the step, so it's like essentially his 1G down with the blood column. So what you're going to see is a lot of stuff going on here. We do, in fact, we briefed all the commercial companies, the FAA and NASA on this, and all the data is available too. So for groups that want to look at the physics of it, there's been quite a number of articles that are written, and we've got 2 modeling programs that have been done on this that are in the process of being published. So what you're going to see here is he does his hand salute. He starts the high-speed cameras that are above him with a little red button, and you'll see him step off, and you'll notice that very quickly, once he's in free fall, he's in 0G, just like he's in parabolic flight. He's basically in parabolic flight for 25 seconds. You see the airspeed, 200, time up here, 12 seconds. He's now at Mach 0.5. Heart rate and respiratory rate stay up 180, 160, 180. I've got all the data too if you want this. I can email you or send you hard copies. Okay, now right about now he's right at Mach 1, right at that point. You can see this little graph over here. He's head down in a right aileron roll. He's at Mach 1.25. Now you see the column of blood moving up to his head as he's in that head down spin. The worst part of the spin, okay, so and he's in the inverted spin for about, and now he just recovered. So he was in the inverted spin that was dangerous with a headward fluid shift of about 2.5 Gs for about 13 to 15 seconds. Very tolerable. We would do spin training to build that tolerance. Acrobatic pilots are used to that all the time. And if you want, I can come back and give a talk on this too, because I have like 1,000 different slides. Anyway, this was not anywhere close to a fatal problem. Okay, we were.
It looked worse than it really was.
Yeah, it looked worse than it was, but he said he was really dizzy. Some people would get motion sick or nauseated from that. It's a big concern. And I could show you some of our other dummy drops where the spin rate was unbelievably bad. There are escape systems in development for several commercial space companies. Yes. Sorry, I know everybody wants to get out of here.
Sorry, I just have one question. To follow on to that, our crew would be able to survive something like this at this elevation or this
Oh yeah,
altitude?
yeah. Now, let me tell you though, this was in free fall without a drogue chute. Our feeling is you use a drogue chute. And all the follow-on tests, that Joe Kittinger said that at the end of this, he said, what we learned was the same thing we learned in 1960 is don't do this without a drogue chute. So the follow-on stuff is a drogue chute, and it cuts the spin down to nothing.
So I guess the question I'm trying to get to is, would all of our crew members be at the same physical conditioning that he was before he jumped, or would we have to be sure of that?
Yeah, that's
He was phenomenal.
He was, and he, I think with some of it's psychological, some of it is physical. You can do spin adaptiveness in acrobatic pilots, including many women pilots, will do this they'll go up and they'll do outside loops and they'll do aileron rolls where they're getting a headward and feetward shift, just like we got. So this is something that an average fit person, and certainly the astronaut population is in that category. Whether a commercial space tourist would be, I don't know. But the drogue chute that we are using now cuts the spin out, so you don't have that problem. That's why we did the follow-on program.
I didn't realize there was a follow-on.
Well, it's a secret, but don't put it on Facebook. Okay. If you have further questions, you can email me. All right, well, thanks so much for your attention. See ya.